Hello, this is Algebra 2, Unit 2, Lesson 7 notes. We're looking at complex numbers and imaginary solutions. So last time we looked at how to figure out how many imaginary solutions you're going to have or how many real solutions. So what we're doing today is figuring out what those solutions look like and how to find them. So to this point, you've seen rational solutions, right? You can write them as a fraction. You could have 2. You could have a half, you could have negative 2/3, and so on, okay? Any number you can write as a fraction, okay? Or even a whole number is a rational solution. Irrational, we've seen some of these recently. We're solving by square roots, and by completing the square, you could have square root of 2, okay? Square root of 2 root 3. These are all irrational because a square root of 2, that decimal, it never ends and it doesn't repeat, okay? You could throw in, we haven't had these as solutions, but you could include a number like pi as an irrational number. You could have a number like e, which we haven't talked about, but relates to interest, okay? So we haven't talked about that just yet, but those can be considered irrational numbers, all right? Real numbers. Right? So real combines any of these, right? So real could combine rational and irrational. Right? So let's look at some equations here and try to solve them and see what happens. So this first example, I've got x squared plus 9 equals 0. Let's solve for x. So I get x squared equals negative 9. Now, to this date, we've told you, okay, go ahead and take the square root of both sides. You get x equals plus or minus the square root of negative 9. All right, so to this point, you've been told, nope, that's no good. Can't do square root of a negative, that's bad. Okay, but using imaginary numbers, we can solve this. Now, some of you are thinking, why do I need to use imaginary numbers? We live in the real world, so on and so forth. But imaginary numbers actually have a lot of important uses, especially in fields like electrical engineering or for electricians. Okay, it's an important concept to help them do their jobs. All right, so it does have some use, although maybe not in your life, but in other professions it does. So let's look at how to use imaginary solutions to solve this. All right, so now we're introducing a number I. Okay, I is equal to the square root of negative 1. Okay, so we can solve this problem now using I. All right, so what I do is I can rewrite this like the same way you'd reduce any radical. You'd break it up into perfect squares. Okay, so using I, negative 1 can be a perfect square, and so is 9. So you take out negative 1, and that turns into I. You take out 9, and that turns into 3. You still have plus or minus 3. So the solution to this is plus or minus 3i. Now, if you consider the previous lesson, we looked at discriminants. Okay, and you found the discriminant of x squared plus 9, you would have gotten a negative value, which would have told you you're going to have two imaginary solutions, or two solutions that are not real. All right? So imaginary solutions, we could have things like 3i, negative 2i. You could also have I root 2. Okay, and so on. Anything with I in it, it's going to be imaginary. Okay? So go ahead and try the next two as practice, and I'll put the answers up. When you're done, you can check them. All right, so look at your answers here. Now, we didn't talk about where to put I when you're solving or when you write your answers. Okay? But if you have a radical, obviously square root of 7 does not reduce. But that negative sign comes out as I. So you have 2 plus or minus I root 7. Some of you might have written I here. That's okay. But our standard convention here is to put I in the front of a square root so that there's no confusion about is it square root of I or something like that. So put the I in front of the square root. Same with this one here. Now if there's a number you pulled out, you put that with the I and put that in front of the square root. Okay, and you can write your answers just like that. So again, you're noticing that there are two solutions here. Okay, there are two imaginary solutions. They come in pairs. You can't just have one imaginary solution and one real solution. It's all or nothing in terms of quadratic equations. Okay, so this leads towards a conversation about different types of numbers. All right, so complex numbers. Well, complex is a combination of real and imaginary. And you can write them in the form of A plus BI. Okay, and what this is A is the real component of this number, and B is the imaginary component. You could have numbers like 3 plus 2i. You could have 0 plus 2i. You could have 3 plus 0i, and so on. Any real number that we talked about at the top of the page would go here. Okay? And the imaginary number comes second. You could have minus as well. It could be 3 minus 2i, and so forth. Okay? So this is a complex number. Any number can be complex. This is all encompassing for any number you've dealt with. Any real or imaginary number is considered a complex number. And this is how we write it. You write the real component first and then the imaginary part second. Okay? So, again, related to what you learned about the discriminant and what we just looked at again with our solutions here with being plus or minus when we do the square root, or if you solve by quadratic formula and you have that plus minus, you're going to see that you get two answers. All imaginary solutions are going to come in conjugate pairs. Okay, you're always going to have two imaginary solutions, 2 or 0, so 0 or 2 imaginary solutions. Okay? They're either going to be real or they're going to be imaginary. You're not going to have both. Now, when we look at polynomials, that'll be different. But for quadratics, this is what we're looking at. Okay? So what does this mean as far as if you have one answer, how do you know what another answer might be? So we might give you something like this, and we'll say 2 minus 3i is one root or one solution. What has to be another solution? Well, this minus was a part of a plus minus. You see this imaginary part. That means we took the square root of a negative, which means the discriminant was negative, which means that there had to be two imaginary solutions. So if we write 2 minus 3i, then 2 plus 3i also has to be a solution. Okay? So take a second and try the next one on your own, and then I'll put the answer up in a second. All right, so you're looking at I root 2. Okay, this is just the imaginary component. This just means that the real component is 0. Okay? So if it's positive I root 2, that means negative I root 2 also has to be a solution. Okay? All right, let's look at this next part, imaginary expressions. So we're looking at I to certain exponents. Okay, so we're going to ask you to evaluate certain exponents. You'll see at the bottom here, we're going to ask you to evaluate expressions that look like this. Okay? But let me explain how this works first. So we're talking about exponents, right? Anything to the 0 power, I to the 0 is going to be 1. Anything to the 0 power is 1. Yes, that includes imaginary numbers, okay? So, I to the first, anything to the first power is itself, okay? I squared, well, we just saw that I equals the square root of negative 1. Well, what happens if we square both sides? Sure, we can square imaginary numbers, why not? Okay, you'll get I squared equals negative 1. Okay, I to the third. Okay, this is a little trickier, but we're going to use some properties of exponents to show this. So I to the third is the same as I squared times I to the first. Well, I squared is negative 1. I to the first was I. So I to the third is negative I. These are very important to remember. You're going to use these to solve any problem like this. So these you absolutely have to remember. Okay? Let's keep going a little bit. What's I to the fourth? You could keep going. I to the fourth, well, that's I squared times I squared. All right, which is negative 1 times negative 1, which is 1. I to the fifth, well, that's I cubed times I squared. I cubed is negative I. I squared is negative 1, so that equals I. So what I'm hoping you guys see is that the pattern is starting over. I to the fourth is the same as I to the 0. I to the fifth is the same as I to the first. So what you see is that you've got a cycle here of 4 values that are going to keep repeating. Okay? And since it's a cycle of 4, it starts over every 4, so any number divisible by 4 is going to be the same as I to the 0 or I to the fourth. Okay? So any number divisible by 4, let's look at I to the 72nd. That's divisible by 4. Okay, it doesn't matter by how much. Okay, if you divide that by 4, there's nothing left over. Okay, so there's nothing left over, so that's the same as I to the 0. Okay, I to the 0 is 1. So I to the 72nd power is 1. How about I to the 33rd power? All right. Well, the closest multiple to that, I to the 32nd, is divisible by 4. Well, 33 is 1 more than 32. Okay? So this is going to be the same as I to the first, which is just I. Okay? Try the next two. See if you can get those. All right, let's look at these answers here. So I to the 42nd. So the closest multiple of 4 to 42 is 40. Okay? So 42 is 2 more than 40. So I to the 42 is the same as I squared. Well, I squared is negative 1. So that means I to the 42nd is negative 1. Okay? I to the 99th. Well, it's close to 100. You know, 100 is divisible by 4, but going over is a little bit trickier. You can think about it that way if you want. But I think it's easier to think of the number below it. So you can look at I to the 96th. 99 is 3 more than 96. So I to the 99th is the same as I to the third. I to the third is negative 1. I to the 99th is negative I. All right, so simplifying imaginary expressions. All right, you'll see some more like this and some more. We'll add some twists to it. All right, but as always, make a note of any questions you have and bring these to class. We'll see you next time.